picking up where we left off last time, talking about the Bohr model, we were talking about what do atoms look like what's their structure. And it turns out that atoms, in the Bohr model, have a nucleus right smack dab in the center, and that's where all of our protons and our neutrons live, our really massive subatomic particles. And then our electrons live on these tracks that we call orbits. And the further away on that track you are, the higher energy that electron has. And those tracks continue to go further and further out. And we got to the idea of these orbits from the emission spectra of different elements. So if you heat up, if you add enough electricity, enough energy to an element, you can get it to make colored light, like neon lights. And the wavelengths that correspond to the distance between these tracks, as it turns out, corresponds to the wavelengths of those visible lights. And we talked about it a little bit on that previous slide, but I also have this one that shows these gaps as well. So looking at specifically, this is for hydrogen. So this is our hydrogen emission spectrum. So basically, what would it look like if you took a neon light, but you filled it with hydrogen instead, and then took the light that came out of that, separated it out with a prism so that all the wavelengths of light separated out real nicely. And you can calculate, you can figure out the wavelength of these colors of lights. And these wavelengths of light correspond to transitions between our orbit levels. So red being next to infrared, infrared's not high energy, it's low energy. The violet part, that's the high energy. Right, so our red side is going to be our lowest energy, and the lowest energy jump that I'm showing here at least is N2 dropping down to N1. So we're dropping from a medium level to our lowest level, and there's an energy difference associated with that. In order for that electron to lose that energy, it has to go somewhere, and the way that it does that is by emitting a photon. This is sort of like glow-in-the-dark stuff. So glow-in-the-dark stuff, you take it out, it absorbs energy from the sun, and then you take it somewhere else, or you just look at it, cup your hands and look at it, and it's emitting energy as well. That's sort of what we're doing here, but rather than absorbing light, we're putting it in as like electricity or something. And then we can see for our kind of like cyan, light blue track, our next color over, that's a longer, it's a shorter wavelength, it's a higher energy, higher frequency wavelength of light, and it has a longer jump. This might correspond to moving an electron from our n equals 3 orbit down to our n equals 1 orbit. And since the distance between those tracks is bigger, the amount of energy that it takes to drop that distance is also bigger. And the same thing holds true for the other colors that we see there. It also takes more energy to get the electron up into that n equals 3 level. So bigger change equals more energy. One of the things that was really great about the Bohr model, notice we're using the past tense, this isn't our current model, but what was great about the Bohr model is that it predicted the lines of the hydrogen emission spectrum. So it didn't just say, yes, this fits with the lines that we're seeing, but it can actually be used to predict them as well. However, it only worked for hydrogen. Didn't work for the other elements. So even if you just move up to helium, just adding one more electron, it doesn't work. If you use helium but you take an electron off, then it works. And so we replaced the Bohr model, named after Niels Bohr, with a more sophisticated model called the quantum mechanical model. So we are learning a little bit, just a little bit of quantum mechanics in this class. So it's enough that you can say, we're learning about quantum mechanics in class, and you can sound really cool. You can sound really smart to your friends or family, and just hope that they don't ask you to tell them anything about it. So we're going to be changing some of the ideas that we've been talking about. So don't just throw away the Bohr model, but we're going to be kind of adapting that material. It could be sort of like a fan fiction, maybe. We're just adapting it. We're using it in a little bit different way. We're slightly changing the names for copyright reasons, maybe. It's actually not for copyright reasons. And so we replaced the Bohr model with the quantum mechanical model. And it's revolutionary because electrons do not behave like particles. Electrons, notably, somehow we think of them as particles. They are not, in fact, particles, or they don't behave like particles. And so we are replacing a couple of things. Orbits are now orbitals. So where we had those nice, neat tracks that our electrons were flying around on, our orbitals are probability maps. For us, we can just think of them as shapes. Not shapers, shapes where our electrons live. And shapes where our electrons live works nicely because all of us hopefully live somewhere, ideally in a house or some other sort of covered dwelling unit. And even though we live there, we are not there right now, I hope. I hope you don't live here at school. I do, but in my office. And so these are shapes where our electrons live. We usually find them in their house because, like us, they like to be there in their homes, but they're not always there. So that kind of plays into that probability part. And we have some fun quotes from famous people to really get us excited about learning about quantum mechanics. So we've got from Niels Bohr of the Bohr model, anyone who is not shocked by quantum mechanics has not understood it. Very fun. Thank you, Niels Bohr. Erwin Schrödinger, the guy with the cats. I don't like it, and I'm sorry I ever had anything to do with it. Very good. We will relate to you, Erwin Schrödinger. And from the great physicist Richard Feynman, I think I can safely say that nobody understands quantum theory. So just to help drive home the point that yes, it's confusing, yes, it's difficult, we're going to be just covering a little bit of it. We're going to keep it very surface level to do a robust explanation of quantum mechanics at like an undergraduate level. We would have to invoke lots of calculus, and I don't want to do that, and you don't want to either, and so we're not going to do that. So we're just going to focus on the concepts, like orbitals, little homes that our electrons live in. So that change from orbits, with Bohr, we had our nucleus, and we had our little tracks, our n equals 1, n equals 2, n equals 3, etc. And with quantum mechanics, we have an orbital and its shape. We've got several shapes. These shapes show us where our electrons are likely to be found. So where our electrons might be. This is a little bit like if you have a friend, would be nice. If you have a friend, right, and you know where they live, and you know kind of their job and what sort of things they do for fun, on any given day you might be able to predict where your friend is. You might guess, oh, my friend's probably at home, it's his day off, and yesterday was his like last day of 3 days of work on, so he probably went out and partied, and so he's at home recovering. And that could be true most of the time. He might be at home. He could also, she could also just be out anywhere else. You could be completely wrong. And so that's sort of what we're doing with these orbitals. Like we know where they're probably going to be, but they very well could not be there. And we also wouldn't be able to pin down like, oh, they're in their bedroom right now. or oh, they're in this part of the house, right? We just have kind of a vague idea of where they probably are. And our orbitals are a little bit more special than our orbits, and so we have both a number and a letter that go along with specific orbits. And replacing that lowercase n is lowercase n, which is our principal quantum number. So this is like the orbit number n. It's an energy level. So we can still think of n as energy levels. A higher n number means more energy. And just like with our orbits, we start with n at 1, and it increases in integer values, so whole numbers counting up. And then within those energy levels, if we're thinking about the orbits, within those energy levels, we have different subshells. Subshells are the shapes. So we've got our principal quantum number. I'm going to abbreviate quantum number as Qn. That's our energy levels. And we've got a subshell, and that's our shape. Our options for our shapes are S, P, D, and F, in that order. Give you some time to write. All right, so we've got our lowest energy orbital. Our lowest energy orbital is 1s. One s is the lowest energy. It has the combination of having the smallest number for its principal quantum number of 1, so it's our smallest n value possible, and it's also the S shape. S is the lowest energy shape, or it's the first shape at least. Our orbitals, since we exist in a three-dimensional space, our orbitals are also three-dimensional in terms of their shape. Very conveniently for us, for our s orbitals are spherical. So S for spherical. So we can think of it as just a ball. And most of the time, in this three-dimensional ball that we've got here, most of the time our electron is going to be inside of that shape. The larger or smaller, like the size that you make that shape, increases or decreases the probability. We're not worried about that. You should just know 1s is a sphere. It's the lowest energy of our orbitals. We also can talk about some other concepts now. So we've established that 1s is our lowest energy orbital. If hydrogen is undisturbed, if it's just in its normal state, a single hydrogen atom, not in its diatomic elemental molecule, it has 1 electron, and it's going to put that 1 electron into its 1s orbital. We call that the ground state. the ground state is the lowest energy state. So if we have a bunch of different options, if we're thinking about our orbits, because that sort of still works here, right? We've got our circular tracks. We can put a certain number of electrons into each of those tracks, and our lowest energy, our ground state, when they're all in the smallest number possible. So they're kind of packed in and condensed. And that's how they exist most of the time. If you give them energy, if you give an electron an energy, it will jump up to a higher energy orbital. And that's an excited state. So our excited state is an elevated energy state. After a full night, or most of a full night of being in my bed in my ground state, I have enough energy to wake up and come here and kind of turn the filter off and talk about chemistry for an hour and 15 minutes. So I'm in an excited state right now, and the caffeine is certainly helping. All atoms, every atom is going to have one ground state. There's one best way to pack the atoms or the electrons in an atom. There's one lowest energy configuration, but there's many, many excited states. Even if you just have one electron, you can bop that electron up one level. You could bop it up 2 levels, 3 levels. It could be in alternate states within those levels. So there's a lot of excited states. There's only one ground state. Atoms are orbitals. Our orbitals show up within a principal shell or a shell of different orbitals in a principal quantum number. So for principal quantum number n equals 1, we just have one subshell, one shape. When we bump up our energy level to the n equals 2, to our principal quantum number 2, within that energy zone, we've got 2 subshells. We've got S, still spherical, and we also have P, and we'll learn about this soon. So we're repeating that same S shape. It's just that now that we've bumped up to our energy level 2, it's bigger than our 1s. So it exists in a larger form. If we bump up to our 3s is even larger. Our 4s, you guessed it, is even larger than our 3s. So all of our S subshells are spherical. And the N determines the size. So you can sort of think of them as Matryoshka dolls, the little Russian nesting dolls. Do we have any questions so far? Yes?
So the ground state, would it always be 1s?
For hydrogen, our ground state is always going to be, one electron in the 1s. We'll learn about ground states for some of our other elements once we get through orbitals. All right, so our 2p subshell, which also shows up in our n equals 2. So it's still n equals 2, but p-shaped. And it was really nice that S meant spherical. P, unfortunately, doesn't stand for anything, or if it does, I don't remember it. So our p-shaped orbitals have a dumbbell shape. So p is sort of a dumbbell shape. And this is not exactly how they look, but it's a little bit more friendly than the way that they actually look. So we've got 3 orbitals within our P. We've got our PZ. You don't need to know the designations, the little Z, the X, the Y. But just so that you know, in case you were curious, the PZ is the dumbbell with its line running through the Z. So it's aligned with the Z axis. PX, in this case, our X axis is the one that's coming out of the board into the board. PX is the dumbbell with the length across the X axis, and PY is along the Y axis. Again, you don't have to know those subdesignations. You should know that P is dumbbell shaped. You should know that P has 3 orbitals. And each of those shapes has the same energy. So those are our P, or 2p orbitals. A convenient tool for remembering how many subshells, how many of those letters, how many of those shapes you have in a given principal shell or principal quantum number. Of n is that the number of subshells is the same as that n value, at least up through 4. So in our n equals 1, our lowest energy orbital, or our lowest energy principal quantum number, we just have our s subshell. It's the only one that we've got. When we get down to, or up to, out to, n equals 2, we've got s and p. So we've added those dumbbell shapes in addition to our spheres. When we get out to the n equals 3 shell, or principal quantum number, we add the d subshell. And when we get out to the n equals 4, we add in the f subshell. An important note here, just in case people were curious, for n equals 5 or greater, the number of subshells is still capped at 4. Because we only have those 4 letters, S, P, D, F. But generally, the number of whatever our n is, that's going to be the same as the number of subshells, the number of shapes that we have. So let's talk a little bit about n equals 3. So in our n equals 3, like we saw in the previous slide, we've got our 3 subshells. Our s, that's the spherical one, this time bigger than our n equals 2 and our n equals 1. We see our p show up again, p being the dumbbell shape. Can anyone guess if for our p subshell, the p shape, the dumbbell shape, for n equals 3 or n equals 2, which one is going to have bigger dumbbells? N equals 3 is going to have bigger dumbbells. It's a higher energy level. So we've just expanded the size of the dumbbells. We've got more energy. We can do more curls or more exercises with our dumbbells. Our d subshell contains 5 d orbitals. So for s, we had 1 orbital. For p, 3 orbitals. For d, we now have 5 orbitals. Can anyone guess how many orbitals we have for f? It is, in fact, 7 orbitals. I don't think I have even pictures of the f orbitals because I don't even like them. The d orbitals I think are kind of fun though. All right, so these are the d orbitals. Again, you don't need to know the subscripts. So don't need to know subscripts. So like the YZ or the XZ. So now for our d orbitals, we've got, for the most part, double dumbbell shape. Except for one of them, which is weird. So we've got double dumbbells for 4 of them. In case you're wondering what the subscripts mean, the YZ is in the YZ plane. So in this, for some reason, this is now the y-axis is the out-in, the z-axis is the up-down. So it would be sort of like this shape for that dyz orbital. And then xz is in the plane that's the xnz, and I'm not going to show you the dxy because that would involve me being on the ground. And then the dx squared y squared is along the x and the y, so it's rotated from our dxy. And then for dz, we've just got one dumbbell, and we've got a donut shape, a torus, that's around the donut shape, or that is the donut shape around the dumbbell. You don't really need to know these, so like if you want to just block this out from your memory, that's mostly fine, but you should know that there's 5 orbitals, and I think it's a little bit easier to remember, like if we know some things about them, maybe some of it'll stick. Any questions about our shapes, our subshells? All right, we're having a good time. So electrons, talking about ground states, getting back to ground states. So we talked about for our ground state hydrogen, our lowest energy hydrogen, we just have one electron, because it's hydrogen, and that one electron is in the 1s orbital. We can show where our electrons are with an electron configuration. So our electron configuration shows where the electrons are in the atom, with like their energy level designations and like what shape they're in. So for ground state hydrogen, we have our lowest energy orbital of 1s. We're always going to start with 1s. And we only have one electron. And so we put a superscript of 1 after the s. So for hydrogen, our electron configuration looks like this, just 1s1. We can also do a graphical representation. So this is sort of analogous to an electron configuration. This is an orbital diagram. So this is similar information. It's just a little bit more. So this is similar information to our electron configuration. However, we're showing an extra property. We're showing our electrons as arrows. So we've got a box that represents our 1s orbital. Box represents the 1s. That's why we've got the 1s underneath it. And the arrow is the 1 electron. We have 2 options for electrons in orbitals. What direction is that electron pointing? Up. Up is one of the options. The other option, any guessers? Yeah, up and down. Typically, in my experience, we're going to write up first. I don't think that there's formally a reason that we can't do down first. I don't think that there's like a quantum mechanical reason for it. If there is, you'll learn about it later in the future, and maybe your instructor will tell you, oh yeah, your intro Gen Chem instructor was an idiot. It always has to be up first. And then you can send me an email, hey Mr. K, you're an idiot. This other person with a PhD told me so. And okay, that's fair. All right, so in our orbital diagrams, the direction represents electron spin. So our direction of the arrow is the electron spin. And conveniently for us, formally the two options for electron spin are up spin and down spin. It's actually up and down. I'm not just making that up, I promise. And related to that idea, we get our first of two rules. The Pauli exclusion principle, named after somebody who I think their last name was Pauli, not a parrot. So our orbitals may hold no more than 2 electrons. So we're learning here max 2 electrons per orbital. And they must have opposing spin. So no more than 2 electrons, that's the max of 2 electrons, and they have to have opposing spin. So some possible options that we might see. We're going to do a couple of things. So we've got 3 orbital boxes shown here. I will usually show them as arrows. So one up, another up. Not allowed. That's illegal. We cannot do that. Quantum mechanics forbids this. We can also have another one that's illegal, 2 down arrows. Also not allowed. However, we can have 1 up and 1 down, and this is allowed. This is what we do. So if you're going to have 2 electrons in the orbital together, they have to be opposite spin, 1 up, 1 down. We can also write electron configurations and draw out orbital diagrams for things that are bigger than hydrogen. So I will show you how to do these. So for helium, helium is He on our periodic table. If we take a glance, take a gander at our periodic table, we'll find that helium has the number, atomic number 2. That also means it has 2 electrons. The 2 there meaning it's got 2 protons. In order for it to be neutral, it has to have 2 electrons. Does anyone remember what our lowest energy orbital is? It is the 1s. So we've got 1s for our lowest energy orbital. And how many electrons can we put into a single orbital? 2. We can put 2 electrons into a single orbital, and so we have 1s, 2. That's our complete electron configuration for helium. We've used up both of our electrons. They've both been housed They both live in a spherical house. So that would be our electron configuration. Now on to the orbital diagram. Since we did the electron configuration, that makes it easy for us to do an orbital diagram. We already know where our electrons are going. We just have to make sure that our spins work out with each other. I usually don't write out a full box because that's 3 extra lines. I'll usually just write a flat line. And then we have to put 2 electrons into this box area. And because of the Pauli exclusion principle, that means we have to put, if we put one up, then we have to match it with one that's down. So that's our orbital diagram. Questions? All right, moving on to lithium. Lithium is one of our alkali metals. It's number 3 on the periodic table. How many electrons does lithium have? Lithium has 3 electrons. And where are we going to start putting our electrons? What orbital? The first one, 1s. So we're going to start with 1s. And we can put, as we saw earlier, 2 electrons into our 1s orbital. However, now we have 1 electron left over. So we have to make a decision. Where do we go next from 1s? We're in the n equals 1, so we only have 1 subshell, only have 1 shape, only have 1 letter. So 1s, that's our only option, our only orbital in our n equals 1, so we have to bump up to our n equals 2. So starting with n equals 2, our lowest energy shape, still s. So we're in 2s. It's our next energy level orbital. And we only have 1 electron left, so we'll put that 1 electron into our 2s. So 1s2, 2s1 is our electron configuration for lithium. Then we can do our orbital diagram. So we've got our 1s box or platform. We've got 1 up, 1 down, so that our Pauli exclusion principle is happy with us. And then we've got our 1 box representing our 2s. And we've got 1 electron in there, and so we'll put a single up arrow. If you want to draw double-headed arrows, I don't have any problems with that. But it is 1 extra line for every arrow, so time saves, time's money, unless you're me and you're just sitting around doing nothing. Maybe that's just wasting money. Any questions about those electron configurations or orbital diagrams? Yeah?
How did you know, I might have missed it, but lithium has 3 electrons and helium has 2?
Yeah, so lithium, the Z equals 3, the Z being our atomic number. So from the periodic table, the number that's up top, it should be just right above the symbol. Right, so that's the number of protons. So 3 protons. In order for it to be charge neutral, it has to have the same number of electrons. So 3 protons, 3 electrons. And that will always be the case for neutral elements. And I don't think we do anything with ions in this class. All right, so when we have multi-electron atoms, our subshells don't have the same energy. So our shapes don't have the same energy because of the way that they interact with each other. And so this is an example of what an empty electron diagram might look like. We've got energy on our y-axis, so our lowest energy things are down below. And we've got things separated out by our S in this left column, our P in the next column, and then our D in the third column, just to kind of space things out a little bit. And we've got individual boxes representing each of the orbitals within our subshell. So for our S, we've got one orbital. It's just the spherical one. For our P, we've got our 3 orbitals. Those are the 3 dumbbell shapes. For our D, we've got 5 orbitals, the double dumbbells plus the one with the donut. And if this looks like a lot, it is a lot. We aren't typically going to be doing this much stuff. This is kind of just to show you there is an energy order. There is an energy order to the orbitals. So there's a generally correct order. Yes, question?
So if you max out your 2s, you move to 2p instead of 3s?
Yeah, so if we were to fill up this 2s, then we would start putting electrons into our 2p for our ground state, because that's the next highest energy level. And then we go up to 3s, then 3p, and then we break that trend that we just set, and we actually move to our 4s before we fill up our 3d. And if this looks really confusing, it is kind of confusing. This is not the only way to know the order of the energy levels. This is just one tool that you can use. And generally, you won't be doing these things in undergraduate chemistry, unless you take inorganic. Then you'll probably do some of that. All right, let's do an electron configuration and orbital diagram for carbon. I'm going to give you a little bit of time. See if you can come up with the electron configuration and orbital diagram for carbon. Our energy order is this. And that's more orbitals, more subshells than you'll need by a lot. So coming back to our electron configuration and orbital diagram for carbon, if we find carbon on our periodic table, we'll see that carbon has the number 6 above it, meaning it has 6 protons and therefore also 6 electrons. So for doing our electron configuration, we're going to start off with our lowest energy orbital, which is our 1s, and we can fit 2 electrons into that subshell. So now we've used 2 electrons, and our next energy is 2s, and we can fit another 2 electrons into our 2s orbital. After our 2s comes 2p. We have 2 electrons left, and we can fit those within our 2p subshell. So we've used up all 6 of our electrons. So our electron configuration is 1s2, 2s2, 2p2. And drawing that out as an orbital diagram, we've got our platform for our 1s. We'll put an up and a down. We've got our platform for our 2s, another up-down. Love getting up-downs. And then we've got our 2p, And our p subshell has 3 orbitals. It has 3 separate shapes, the dumbbells that are along the axes. So we've got 3 different boxes there for the 3 orbitals. And we are going to put these in up and up. And the reason that we fill them in up and up is because of Hund's rule, our second rule. So for Hund's rule, when we're filling orbitals of equal energy, same n and subshell, like 2p, 3d, 4f, etc., things that have multiple shapes instead of just a sphere, we're going to fill those singly first and with parallel spins. So we'll look at an example of what filling in the 2p incorrectly would look like here. So one way that we could do it wrong is matching them up. And they're not going to match up, right? We've got extra space for these electrons to spread out. They're not going to want to pair up and be constrained. So that is not going to work. And the other thing that we don't want to do is put them in separate boxes or separate orbitals with opposite spin. There's some energy that comes along with being in sync, being aligned, being parallel spin. And so they're going to want to sync up their spin. Synchronized spin is more stable, in case you're wondering why they don't go opposite spin. Another check. Any questions? Yes?
When writing the things with multiple orbitals, you always put as many lines as there are orbitals?
Yes,
Okay.
as many lines as there are orbitals. So if we were filling up in our 3D, I would have 5 boxes to represent the 5.
One electron.
Even if there's just one electron, yeah, we still want to show all of the boxes. Other questions? All right, we are going to learn about another way that might be helpful for you for thinking about all of these things. So we can think of our energy levels as rooms in a hotel. So this is electrons in Mrs. K's chemistry land at the Quantum Hotel. Mrs. K not being my wife, but my mother. So Mrs. K's chemistry land, she runs chemistry land. So in the Quantum Hotel, we've got a bunch of different floors. Our floors here are the principal shells, so the different numbers. We've got a first floor, lowest energy, our second floor, higher energy, third floor, even higher energy. And we've got a bit of an upside down pyramid scheme to our hotel. So it looks something like this, and the electrons enter starting on the ground floor. And in our n equals 1, we've got one room, and we can fit in each room, depending on the letter of the room, a certain number of beds. Our beds are the orbitals. So at our n equals 1, it's our smallest floor. We just have one room. We've got our S room. Our S room only has one orbital. We can fit 2 electrons in there, or 2 people. 2 people to a bed. That's the rule. They're not big beds. Once that bottom floor fills up, our electrons are very stingy with their money. They're trying to save. They're not trying to go straight to the penthouse. They're going to fill in the next level of rooms. So once the 1s is full, they have to fill in then the 2s and the 2p, and we can get people into those rooms. Our S rooms each have 1 bed. That's our orbitals. Our P rooms have 3 beds. And one of the ways that I think that this is helpful is for thinking about our Hund's rule. So our Pauli exclusion principle says that we have 2 people per bed and they must have opposite spins. Our Hund's rule says that they They fill in singly first, and then they double up. So let's think of a scenario. Lots of us have probably been in this situation, right, where we have our hotel room, and we're on a bit of a budget, and so we're sharing a room with some friends, and we're looking at a P subshell room in this case. If any of us is going to a hotel room and we're taking 2 friends along with us, so there's 3 people and there's 3 beds, what's the logical way to arrange people into those beds? 1 person per bed. We all want to spread out. We want our own bed. And so you're going to put 1 in each of the beds, and most likely you're sleeping with your head to the wall because you're not a psychopath. And so everyone's going to be sleeping the same way in their beds with their heads to the wall, because that's typically how people sleep. You might be a psychopath, sleep with your head to the door. I did that for a while. If we have extra people in our hotel room, unfortunately we can't call down to the first floor and say, hey, do you have a carry-away bed or something that we can get somebody in here? They're just going to have to pick one of these beds, and for whatever reason, these people are very insecure about sleeping in a bed with another person, and so they're going to sleep head to foot like we all do, right? I don't know how the coverage situation works for that, but that's how they're arranging themselves in the beds in that room if they have to. But if they're given the choice, it's all lined up, heads along the wall, nice and cozy. So that's maybe a way that you could think of the way that our electrons go in, and let's not worry about that, because that was just the energy diagram again. Sort of a look at the quantum hotel, I guess. Okay, so we know from this energy diagram that I'm not going to give you on an exam, by the way. We know what our energy level filling order is. We can read it off, right? 1s, 2s, 2p, 3s, 3p. That's a lot to memorize. So here's another tool you can use instead. So in this tool, we've got our S, P, D, and F subshells as our columns arranged next to each other. And then we've got our N numbers of 1, 2, 3, 4, etc. And in our 1s, we've got 1. We don't have a 1p or a 1d or a 1f, so those are empty. For our n equals 2, we've got 2s, then 2p. No 2d, because that doesn't exist. Then we've got 3s, 3p, 3d. No 3f, because again, that doesn't exist. And the way that you would determine the energy filling orbital, or the orbital filling path from this, is these down left arrows. So we cut through at this diagonal path. That's our orbital filling order. So we've got our 1s, our next arrow cuts through 2s, our next arrow cuts through 2p, 3s, our next arrow cuts through 3p, 4s, then we get our 3d, 4p, 5s, etc., etc., etc. This works. This is a valid tool, a valid method. You do have to learn the tool. So if this is something that you want to learn, you're interested in using, you're welcome to do that. This method works. It's not my favorite. I do think it's cool. But if you have a periodic table, which you will have a periodic table on every exam, there's arguably a much better way of figuring out the order. If we're going to do the order from the periodic table, we need to learn some zones on our periodic table. So our zones are color coordinated here. So in our blue, we've got our S block. So that's all of our alkali and alkaline earth metals. So that's our S block, all the way on the far left of the periodic table, our S block. we also have our P block. That's the far right side of the periodic table, this giant rectangle, everything to the right of our transition metals. Our transition metals, here in orange, go Tigers, that forms our D block. And then the one that we're not going to use is the F block that usually gets pulled out and set below the periodic table. Any questions about those blocks? I'll show you how to use them in a second. So I would recommend memorizing these blocks. And I don't remember, okay, there's some stuff on the next slide. So the way that we can figure out our energy orbital order is using these blocks. And we're just going to count up. Just counting up by the element number, the Z number. Another important feature to note here is that the row, or period, as it's often called, is N. So we've got 1, 2, 3, 4, 5, 6, all the way up to 7. So the way that we figure out the filling order is starting with hydrogen. Hydrogen is in the row equal to 1. So its principal quantum number is 1. It's in the S block, so it's 1s. Helium we think of as also being in here. The reason it's way over on the right side is because it's a noble gas. Helium is also in the 1s. So we get from that 1s. Then we move down a period, and we're with lithium. So lithium, we're in our N equals 2, so we're filling up our 2, and we're in the S block, so 2s comes next. After 2s, we jump across our D block to boron. And with boron, we're still in our N equals 2, but we're in the P block, and so we're filling up 2p next. Then we jump down another row. We're in N equals 3, still in our S block, or back in our S block. So we've got our 3s, jump across. We're still in N equals 3, but now we're in the P block, counting up. So 3p comes next. Then we jump down to N equals 4. We're in our 4s, so 4s comes next. And then we get to our first row of the D block. When is the first time that the D subshell shows up? What N number? Not what period number, what N number? What principal quantum number? It's not 4. It's not 5. It's 3. D is our third subshell. It shows up in N equals 3. So for that reason, this top row of our D block is labeled 3D. So we fill up 3D, then we get over to our, 4P. After 3D, we're in 4P, and the trend continues counting up like that. So the only really tricky thing, I think, for using this method to figure out the order, this is the correct order, by the way, is remembering for our 3D, the first time it shows up, this top row of our D block is 3D, not 4D. So it's one less in the D block than the period number. So the first row of D block is 3, not 4. And that, I think, is the only real tricky part about this. If you got to the F block's 2 less than the row number. We will not touch the F block in this class. And we'll be doing some examples with this probably next class. Okay, so a little summary of some of the stuff that we've been talking about. We're going to fill our low energy orbitals like 1s, 2s, before we fill in our higher energy orbitals, like 3s, 4p, etc. Not necessarily in that order. Our orbitals can only hold 2 electrons each. And they have to have opposing spin. So 2 electrons per bed with opposite spin. If we have options, we're going to spread our electrons out. And that's our Hund's rule. So we'd fill them in singly with parallel spin if this is in our 2p, if we had one more electron that we had to put in there, then we would start pairing them up. But until then, we just fill them in singly with parallel spin. Questions about stuff that we've gone over so far? All right, let's do electron configurations and orbital diagrams for some bigger things: nitrogen, oxygen, fluorine, and neon. So first up, nitrogen. If we look at where nitrogen is on the periodic table, the path that we would take to get there, all of the elements that we would have to run through to get there, hydrogen and helium, are in period 1 and in the s block. So that's going to be our 1s. So for nitrogen, we have to get through 1s. We've gone through both of the elements in the 1s, representing 2 electrons. After that shows up row number 2. So now we're in 2, and we're starting again in the s block. We are past the s block. That means that the s block is full, so 2s is full. Nitrogen is our third element in our row 2, so 2, and then p block, so 2p. It's the third element, and so it's the third, or it's got 3 electrons in the 2p subshell. So that's the fast way of doing electron configuration. The longer way to do it would work out the order and subtract off the number of electrons at each step. Let's look at oxygen. Oxygen is 1 spot over. It's got 1 extra electron from nitrogen. So all we do is we copy this electron configuration and we add 1 more electron. So we're still going to have our 1s2, our 2s2, and we are in the second row of the p block, or first row of the p block, second row of the periodic table, so 2p. We're in our 1, 2, 3, 4th position. It's the 4th element in. 4 electrons go into our 2p. You might be able to guess then that fluorine, 1s2, 2s2, 2p what? How many electrons in the 2p? 5. And neon, being the last, being a noble gas, being the last element in that row, is going to represent the full n equals 2 principal shell. So now we'll have 2p6. And our orbital diagrams are going to look very similar for these. For our 1s and our 2s, those are both going to be filled up and down. For all 4 of these. So we'll just sloppily copy and paste those so that we can get on to the good stuff. So for our 2p, we've got 3 orbitals, the 3 different dumbbell shapes. For nitrogen, we've got 3 electrons to place into our 3 orbitals. So we're going to pair them up, 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 fully spaced out according to Hund's rule. And then for our oxygen, we're adding 1 more electron. So up, 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 down for oxygen. For fluorine, up, 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 down, down. And neon is here just winning. Up, down, up, down, up, down. Questions? But wait, that's not all. We can do another one. So you can imagine, right, this is just going through the first 2 rows, the first 10 elements. Basically, we've done most of those electron configurations. What if we were doing an electron configuration for like PO down here, number 84? We would be filling in just so many of our energy levels. We'd be writing out so many orbital diagrams. Fortunately, we've got a shortcut method. So here's where we're learning that shortcut method. So the electron configuration of the previous noble gas, the one that's up 1 row from whatever element we're doing, can be abbreviated by the symbol in brackets. So that can save us tons of time, especially if we're doing electron configurations for really large things. So let's show what that looks like for sodium. Sodium is Na. It shows up in period 3, or row 3, and it has 11 electrons because it has 11 protons. So our shortcut is the row 2 noble gas. And our row 2 noble gas, looking all the way at the far right side of the periodic table, is neon. So in brackets, we're going to place capital N lowercase e, and that accounts for our 1s2, 2s2, 2p6. So that's all woven into our symbol for neon here. How do we figure out how many more electrons to place? A couple of ways. One, if you just look at the periodic table, the next thing after neon is our row 3 in the S block. We're in the first position. That's going to be 3s1. That's how I would read it off, but I've got a lot of practice doing this. Another way to do it is take a look at the number of electrons that we have. We've got 11 electrons for sodium. 11 electrons for sodium. Neon has how many electrons? Neon has 10 electrons. So by using that abbreviation, we've accounted for 10 electrons. 10 electrons have been used. So we have 1 electron left to place. And according to our periodic table of the elements, after neon, we're in our N equals 3, and we're in the S block for our next energy level. So we're filling in 3s1. Okay, last chance for questions. All right, we will wrap up there and pick up with more fun on Thursday.